All right. Hello, everyone. Once again, um, thank you all for joining today. And for our webinar, let me just share my screen before we can even start. For the remaining of the presentation, I would have to turn off my camera, primarily because my internet connection might be a little bit slow where I am. And one moment, so we can start. Great. I hope you can see my screen. You should be able to. In any case, once again, thank you all for joining our webinar on introducing parametric carbon analysis in early design. My name is Vasilis Kalfounzos. I'm an LC engineer and a business developer at OneClick LCA. My background is in civil engineering, and I have a master's degree in environmental engineering as well. And my focus has been on how we can lower embodied carbon through early stage material optimization and parametric design practices. Today, I'm joined by my colleague, Johanna Järvinen, who will be taking some of your questions and helping me out in general here. And the agenda for today is fairly simple. The webinar is scheduled to last about 40-45 minutes. We'll start with a very short introduction about OneClick LCA, then a few words about embodied carbon and early design, and then we will spend the remainder of the time in Grasshopper doing a demo with OneClick LCA. And in the end, we will have a Q&A session where I'll be able to take all of your questions. If you come up with any questions during the webinar, please use the Q&A function, and so that I'll be able to see them in the end. So about us, who we are OneClick LCA. We were founded in 2001, and over the past decade, we have been developing software solutions that, to put it broadly, help decarbonize the construction industry. We have different solutions depending on the needs. We have software for whole building lifecycle assessment, software for product LCAs and EPDs, and also solutions for greenhouse gas reporting, so more towards the corporate responsibility side of things. We're a global software. We're being used in more than 100 countries right now all over the world. We support pretty much every green certification and local compliance scheme available out there. Of course, that includes LEED, the Living Building Challenge, every net zero compliance requirements. And we do have the largest construction materials database available with more than 100,000 data points right now. 30 to 35,000 of them are specific to North America. On top of that, we also do whatever we can to help transform the market. This is why we offer a lot of services such as trainings, webinars like this one, and also we do a lot of low carbon construction policy work, primarily because we work with institutions and regulatory bodies that work towards that end. Okay, 1 second, there we go. At OneClick LCA, we are trying to integrate the entire ecosystem under one platform. This is why we support every regulatory scheme. We support every certification available. We integrate with pretty much every major BIM and PEM software out there. That includes Revit, Rhino, Grasshopper, as we will see today, IS, Design Builder, you name it. On top of that, though, we also offer a holistic set of tools. Of course, embodied carbon accounting is one of them, but we also have add-ons for lifecycle costing and building circularity assessments. And from the product side of things, we have, as I mentioned, software solutions that allow you to do product LCAs and make EPDs, which you can then use in your building LCAs. Now let's move on to the key topic of today's presentation, which is none other than bringing embodied carbon in the forefront and primarily within the early stages. Before I say anything else, I just want to talk a little bit about the different scopes of carbon accounting and what do we mean when we talk about embodied carbon, since different certifications and regulations use different scopes. In a nutshell, embodied carbon includes upfront emissions related to the materials in the use stage of the project, the end of life, and anything beyond the life cycle. Then we have whole life carbon. And in that case, we are simply introducing operational emissions in the equation. So anything operational energy consumption and water consumption as well. And then lastly, we have embodied carbon emissions, which include the life cycle stages A1 to A5. So the impacts from the manufacturing process of the materials. Then we have life cycle stage A4, which is the transportation from the manufacturer site to the construction site. And then lastly, the construction processes. In the use stage, we talk about life cycle stages B1 to B7, and these include material replacement, material repair, and also operational energy consumption, water consumption. And then, as previously, we have the end of life, which are life cycle stages C1 to C4, and then anything beyond the building life cycle. So let's try to put the things into perspective. Stopping the climate warming to about 1.5 degrees requires approximately 35 gigatons of CO2 equivalent worth of additional actions. What that means in practice for us is that all the existing practices that we have in place, we will have to revisit them. And basically, they are not enough. We need to come up with new ideas on how we can reduce our emissions. Buildings are responsible for about 39% of the global carbon emissions. 28% of them come from operational emissions, so anything in the use stage from energy consumption, and then the remaining 11% come from the materials and the construction. The issue here is that these 28% from the operational emissions are being reduced over the life cycle of a project. And that's primarily because we are currently decarbonizing our grids. We're using renewable energy sources, and as a result, we're reducing these emissions. But the emissions from the construction process and the materials themselves, once created, they remain there. Cities actually will double by 2060. Creating an additional 230 gigatons of embodied carbon from construction materials allocated, where 40% goes into new construction, and the remaining 66% goes to infrastructure, 6% to infrastructure and renovation. Today, we'll be focusing primarily on new construction, though, and how we can optimize that part. Okay, why doesn't it change? There. Oh. This is just a visual representation of what I just said about operational emissions and why low carbon construction matters. In any case, as we can see, over the lifespan, building operation emissions from building operation are being reduced, while the share of the emissions coming from building materials and construction keeps on increasing. To sum all of this information up, if there is one conclusion that we can take, is that we need to be cutting embodied carbon emissions now. And there are a lot of different numbers out there on how much we should reduce these emissions by, but if we were to take World CBC's result, we should reduce them by at least 40% by 2030. As previously mentioned, what that means is that we should optimize all of our existing practices and also come up with new ideas on how we can improve carbon accounting and subsequently reduce emissions. One idea might be to start doing LCAs for innovation projects and fit outs, as they constitute 30% of the total embodied carbon emissions, or, as we will see today, work with early stage design. So we need to, sorry, 1 second. Something seems to be frozen here. Can you see my mouse moving? Can someone confirm that? All right, great. Thank you very much. So we need to start working on it early. And there are quite a few reasons for that, and I will explain them a bit later. But basically, the earlier we start implementing life cycle assessments, the more opportunities we have to reduce our emissions. Also, the later that we look into LCAs, the higher will be the cost of change, to the point that after some time, it will become prohibitive and we will not be able to basically change anything. So we will just know what our carbon emissions are with no ability to influence it. And let's go here, which is why actually early design is important and what are the main benefits. Of course, there are more, but these are the primary ones. First and foremost, at the early stages, we can examine the shape and the size of our project against embodied carbon. And what do I mean by that is we can have our Revit models, Rhino models, whatever we might have, as simple as possible, and start looking into, okay, how much will my embodied carbon change if I increase the size, the floor height, whatever this might be. At the early stages, we can also influence material assemblies. And usually, when we implement LCAs later on, we're not able to change, let's say, whether we'll be using timber or steel or anything like that. And that's because, as we'll talk later, they are locked. So early on, we can influence those material choices and make the right decisions. We can perform cost versus carbon analysis. We can see how much our changes will affect the total cost of the project, because of course it's good to reduce our carbon emissions, but what if the cost becomes prohibitive? Or is it that worth it, increasing the project cost by 50% and reducing emissions by 20%? These kind of decisions can be taken very easily at the early stages. Then we can optioneer without pre-existing material constraints. This is very closely related to what I just talked about. So at later points, as I mentioned, we have already decided what's going to be the size of the project, what materials will be used, pretty much the quantities as well. Early on, we have the time available at hand to examine these choices in depth. The increased time in consulting hours, let's say, would be minimal, primarily because through additional tools like Grasshopper, for example, we can examine multiple options at the same time. And speaking of Grasshopper, early design allows us to iteratively optimize our designs. We can set up our parameters to whatever we want them to be: energy performance, carbon performance, structural elements, and so on, and all together at the same time find the most optimal solution. Give me a moment, please. One last reason why it is important to look into this is because more and more developers and investors are implementing low carbon limits in their requirements. The more ambitious the target they set, the more important it is to start working on it early so that we can achieve greater reductions. And this is one of the main reasons that very recently we published this report, which is aimed for investors and developers and gives them suggestions on what specifications can be implemented in their contracts. Since we will share this presentation with you later, I have also added a link here, which you can click and directly download the report if you'd be interested in reading it. We've talked about the benefits of doing early design and how it can influence our projects, but let's bring the attention down to the challenges, and more specifically the challenge, which is lack of information. Main challenge when we work early on is that we don't have enough details to move forward. We don't have a bill of materials. We don't know anything about the composition of our project. So it's pretty difficult to set a baseline and work from that point onwards. So it is important to be able to bridge that information gap. Towards that end, we have published an article on our website. Again, you can find it when we share the presentation. There's a link here that will show you how you can modify your BIM practices for LCA automation depending on the level of detail that you're working with. Now, speaking of bridging that information gap, at OneClick LCA we have developed a number of add-ons and software integrations that help you work towards that goal. So let's say you're at the pre-project stage, you can use the Carbon Heroes benchmark that we have on our software to set the limits for your projects and work towards achieving them. At the conceptual stage, you can use Carbon Designer, which is an add-on that we have developed that allows you to create a bill of materials for your project with very minimal amount of information. And I will show you how this looks like in a second. In the design stage, you can use any of the software integrations that we mentioned before, like Revit or Rhino, to get your data and upload them into the cloud and do an LCA. Then in the specification part, you can directly download DPDs from our website. You don't have to search numerous other databases to find the required documentation. Speaking of Carbon Designer, it has been developed for concept phase decision making. The goal is to allow you to take the right direction before even start designing, if you want to, and all that with very minimal amount of information required. Basically, all you would need to know is what building elements you want materials for, the project location, typology, and in the end, the project size. And with just this information, we can give you a project carbon breakdown and an average bill of materials for your project. Just to wrap this presentation up, I just want to bring up LCA within Rhino and Grasshopper using our integrations. We very recently published 2 integrations, one for Rhino, one for Grasshopper. The one at Rhino is fairly simple in the sense that all you need to do is draw the elements you want results for in their specific layers, assign materials to them, and then you'll be able to get results for the geometry that you drew. But within Grasshopper, you can define your building parameters to whatever you want them to be. You can choose the materials you want to use, and then run an LCA within Grasshopper. And in the end, you can see within Rhino's viewport in real time how changing these parameters can affect your project's embodied carbon emissions. If you want to take it then to the next step, you can also use our plugin together with other ones like Galapagos, for example, if you want to optimize your building shape for preset carbon targets through embodied Carbon Heroes benchmark, which I just mentioned, or multi-criteria carbon optimization together with Octopus. Let's say you want to compare cost versus area versus beam deflection versus carbon, all of them together. You can use our plugin together with Octopus to do that. That will be all with the presentation. I just didn't really want to bore you that much. I want to go directly into Rhino and Grasshopper. Show you in a few steps how you can move from just a very basic idea to get some carbon results to a full building when we send our data to one-click LCA. So before we start, the entire process is basically divided into 4 steps. Step 0 is to, of course, have your design ready, which I should have somewhere here. There it is. So this is just my Grasshopper script, very basic building, could be anything from ground floor office to industrial production building, warehouses, whatever you wanted. Right here is my Grasshopper script, and right here are my parameters. As you can see, if I change them, my project's shape changes as well. Then the first step would be to decide which materials you want to use. Right here, I have basically 3 elements that I want to get results for. I have my slab, I have my columns, and I also have my external walls. So I need to decide which materials go where. How we can do this? We go to one-click LCAs tab, and we use the select LCA profile component. For each element that you have, you should have one LCA profile component. So give it a second. There it is. And basically, right here, you can search for a material in our database. And you can search either by using a text panel, say concrete, for instance, connect it to the search profile string, and then the select LCA profile tab will be populated with the results that match those criteria. Or you can use the filters right at the bottom to limit your search results. For example, I want to use North American data, and since I'm looking for my slab, got the material right here. Wait a second. Go to the material and search for ready-mix concrete. So these are all the available material subtypes we have within the software. So let's go to the bottom, ready-mix concrete. There we go. And we want ready-mix concrete for external walls and floors. That looks fine but to me. And right here, you can choose the material that you want to choose. So I'm going to go with a very simple one, 0% recycled binders. That's fine. And I'm going to do exactly the same process for the remaining two elements. So I'm going to copy this one twice, like this. And for my columns, I want to use a different type of concrete. So again, same thing, all the way to the bottom. And should be this one. There we go. And I'll use the same concrete for my external walls as the one I use in my slab. The next step is to connect the materials with the corresponding geometries. And we do this using the define material component right here. We connect the LCA profile, very straightforward, with the geometry. Again, same thing, LCA profile with the geometry. And one last time. There we go. So I suppose most of you that already use Grasshopper can see that there is a warning here. And if we go to the bubble right here, or whatever that is, you can see what is the warning about. So we have to specify thickness or quantity. And why is that? That's because I drew, this is the same error in my external walls as well. I drew my slab and my external walls as surfaces. And the unit I'm choosing here is volume. So for that reason, we have to specify the thickness of them so that we can get the correct results. It's very easy to do that. Just add a text panel with the thickness right here. What I want to bring up is that at the moment, the plugin only supports metric units, but in the next release, which will be coming very soon, we also included imperial units as well. Then I'm going to do the same thing to fix the error here and say 0.2 for my thickness. And that's basically it. We have successfully connected the geometries with the profiles. Now, the next step is to assign a class to each of our materials. How we do this, we use the create construction component. Again, same story all over again, 3 times, like this. We connect the materials, 1, 2, 3, choose the correct class. So these are my external walls, this is my column, and these are my slab. There we go. And the last step is to run the LCA, of course. So we use the run LCA component, connect everything in here, like this. And we have to add a toggle to control whether we want to run the calculation or not, and a button that will allow me to log in using my monthly LCA credentials so that we can actually get results back from the server. So if I click on this one and log in right here, sorry, I now have a rather large name and password, so you have to excuse me. Click on OK, give it a second. So there's a question. I didn't see what was the difference between different types of concrete mixes. Does the software show you the compressive strength to choose? Yes, it does. I will just show you 1 second. So if we go here, for instance, in this material, you get its description. If you want to, you can always add a text panel, connect it with LCA profile, and you will get the name of the material right here. And whenever you change the material, this will update as well. So you will always know what materials you have chosen. One moment, there's another question. Oh, okay. Then, come on, let me run the calculation. Give it a second. My laptop is definitely not made for Rhino or Revit for that matter, so we have to be a little bit patient with it. Okay, should be done by now. Let's give it a few more seconds. Once the calculation is done, we can now see our results within Rhino's viewport by using the visualize results component. Connect strings. As you can see, the 3D model is colored, and you can choose how you want to see the results, either by absolute results or by volume, whatever you would like. Let's go with absolute for now. As you can see, we scroll in there, we get the results. And what I was mentioning about real time, if we change our parameters, the results update as well. Of course, the upside of this is that you can now use, for example, Galapagos to optimize for whatever parameter you want to optimize, or you can use other plugins together with one-click LCA to have a more a complete result. But the sky's the limit, basically up to you. So once we are done with our Grasshopper script, we have successfully chosen which design we want to go with. Then the next step is to send this to the cloud. And before we do anything else, what I want to bring up is that what do we have here? We have just a slab, concrete. We have columns, again concrete, nothing else, and our external walls. So you barely call this a full design. What I want to do now is actually from this idea that I have here, get a full design for my project so that I can start optimizing my material choices. Again, even before we have a developed design. So I will add another button that will allow me to send the model to one-click LCA. There we go. Cloud. Click on the button. And this will start the import process. The import process is fairly straightforward, and it's the same whether you're uploading your data with Revit, Excel files, Rhino, whichever integration you might be using is exactly the same thing. Now, give it a moment to load. There we go. First things first, we have to choose at which project we want to send our data to. So in my case, I have already created one. The next step is to choose a design. I will create a new one. Click on continue. Give this design a name, ch import. And then next, we have to define the scope and the type of our analysis. Basically, which building elements we want to include. In my case here, I'm just going to go with very basic scope, foundations up to enclosure. Click on add. And the next step, the software is asking us how we want to combine our data. Now, this is a very small project, of course. In reality, you might have projects with hundreds, even thousands of rows of materials. So for computational reasons and simplicity, you can combine your data, you can combine identical data points together. The software will always choose the most optimal way for computational reasons. So you're perfectly fine, just leave it as it is. Now we'll click on continue. And the last part is the mapping process. The mapping process is where we match material descriptions with materials from one-click LCA. In my case, since I have already mapped everything within Grasshopper, I have nothing else to map here, and I can see the material description and which resource we're using from one-click LCA together with its quantity as well. So once we are done, we just click on continue. There we go. If there are any mandatory data missing for benchmarking or calculation purposes, you'll get an error right here. I'm just going to fill them in real quick. Set my calculation period to be 60 years. And my building area, that should be okay. That froze. Fine. I suppose that should be, let's say, 6,000 square feet. approximately. I remember it from the previous time I was working on it, so it should be about 6,000 square feet. In any case, this is the results table that we get, but these results are not very indicative because, as I said, all we have is a couple of concretes. So if we go back to our building materials, input data right here, and building materials, we can see what we have used. We have concrete for columns and external walls, and we have concrete for the, what do you call them? The slabs, the floors. How do we go from here to a full design? This is where Carbon Designer comes to help. We go to import data, and we are now going to use Carbon Designer to fill in any information gaps we might be having. What information do we need to know? As I mentioned previously, we need to know what building elements we care about. In my case, I have everything from foundations up to enclosure. We need to know the location of our project, wherever that might be, the building typology. We have multiple different building typologies which you can choose from, the size of the project, number of above ground floors, and that's pretty much all you need to know. If you know additional information and you want to put it in, you can also say you have an underground parking lot, or you can look into the foundations. That's also perfectly fine. We include 3 of the most common types of foundations: steel core piling, footing foundations, and round concrete. Sorry. And sorry. This, yeah, there we go. We can calculate areas. There we go. And we get a shoebox analysis of our project. Again, I need to stress out that this is a shoebox, so just basically rectangle, but we give you the ability to change the areas if you want to. The areas will then be used to calculate the quantities of the materials. So in that way, you can change the shape a little bit to something more complex, but for early design, a rectangle does its job. Now, what do we already include? We include our columns, so I'm going to remove them from my quantities. We included external walls, so I'm removing them as well because I don't want data for them. And we have also included the slab, so I'm gonna take it out as well. Now, when we click on Create Baseline, what will happen is that we generate the bill of materials for this project, and we also give you carbon results for this project, and you can see these results either by building elements or construction groups. And if we scroll down, we have a list of all the different material assemblies that we have used for this project. I can't stress enough that we're talking about material assemblies at this point. So if we go, for example, to the roof slab, we have an entire assembly, not just the material itself. You can change all of them if you want to start making some initial comparisons even at this point, or if you have an idea of, let's say, what kind of beams you might be using, you can also play around with it. So I'm just going to go ahead and change it to steel beams. And what happens is you get updated results and, of course, updated quantities. And in the table at the top, you can also see how this change has affected your project. So I've changed from a concrete beam to a steel beam. Why not? I'm going to click on Set as Baseline to save this, and then Save Design to Query. Because I already had data, what I want to do now is merge them. So I'm merging them, and I've moved from a very simple grasshopper design to a full building just in a few steps. Basically, as you can see, we have a full list, a full bill of materials for our project. And now if we go to our results, we can get much more insightful information. We have results, of course, for global warming potential and for every life cycle stage that we were talking about before. And if we scroll down, we have multiple ways which you can use to optimize your results, from pie charts, bar charts, columns, tree maps, whatever you want to whatever you find it easier to understand your emissions and subsequently reduce them. One last thing that I want to show you is this most contributing materials row right here, which is basically, as the title suggests, a list in descending order of the most contributing materials used within your design. But the interesting part is when we click on source sustainable alternatives, whenever available, we get suggestions on how we can improve our design. All you have to do is basically find which one is better for your project, copy its name and paste it within your design. And that would be pretty much all of it. I don't know if you have any questions, you can leave them in the Q&A chat. So I didn't see what's the difference between different types of concrete mixes that the software. So okay, we've answered this one. What does the climate zone affect the result rather than the actual location? That's primarily because of the insulations that are being chosen, and also because micro differences in the region wouldn't really make that much difference. Any other questions you might have about the Grasshopper plugin, the software, anything about early design? Social cost of carbon and how it is it calculated? So the social cost of carbon, I can share with you the methodology. I will make sure to share it with our marketing department, which would then share you the slides and the article about social cost of carbon. But in a nutshell, is a methodology developed by the EPA. It's a user set value. You can set it within your company profile, and you can basically get the results based on the total carbon you have right here multiplied by the user given value. That's basically it. What is the type of subscription we need to get to have access to this library? So One Click LCA has 3 licensing levels: starter, business, and expert. With all of our licenses, you get access to our database. Now, depending on what you want to do, you might be requiring different license levels. For example, if you want to use our plugins, you'd have to have either a business or an expert license. Or if you want to have access to some advanced benchmarking features, you would then have to also get either the expert license primarily. Does user set cost? Yes, it is a user set value. Typically, it should be decided by the company. Basically, it's a corporate responsibility thing, but yes, you set it yourself how much it would cost. Carbon Designer has a complementary role for missing building info, or sets a baseline to compare iterations against, or both. It's actually both. Primarily, you can use Carbon Designer to start evaluating different design options. You don't even have to go to Grasshopper or Rhino or any software to get a design. Once you have a design available and you're missing some information, you can use Carbon Designer to fill in these gaps. Another question is, what extra results does parametric design gives us over the LCA? I saw that the results were primarily carbon footprint and GWP. Okay, so a parametric design, it's not that parametric gives us additional results over the LCA. Parametric allows us to examine different iterations of a project very quickly by just changing some parameters, which what these parameters might be. This might be the size of the project, the height, it might be maximum beam deflection, any kind of parameter that you would use to design your project constitute a parametric design. Carbon, what we're doing now is we're trying to introduce carbon as a parameter in this process, just as we have daylight, for example, or energy analysis. That's what we're trying to do. So in the end, the results that you would get in terms of carbon emissions still are global warming potential. But what you would have achieved is that you would have managed to evaluate multiple design, multiple options, and arrive to the optimal solution. Exactly. Parametric design would be very helpful at the early stages, where you don't know how your project would look like. You don't have an idea of what the composition would be. So you're looking into many different aspects, many different items together at the same time to find one good iteration that would be useful for you. Thank you as well. So since we don't have any other questions, I would like to thank you all for joining today. I really appreciate your time, and I hope that you found everything useful. And see you all soon. Have a great day.